Alright, hello and welcome back. My name is Cameron Kirk and this is another video in my series on DE10-Nano projects. And in today's video we are going to be going over not this one. It is the designing and flashing the design. So the name kind of sounds boring, but really this is going to be our first time writing C code that will control a component we implemented in Verilog on the FPGA using the HPS to FPGA. So this one is a pretty important video. Just to give you a brief look of what it's looking like, we're gonna do some stuff. Here is the C code. Let me get out of the way here. Here's the C code, and one of the new things that I got exposure to in this is using these Linux syscalls. So like open and the mmap, I've never used those before, but we're going to get some exposure to that in this tutorial. One thing that I have got to recommend right out of the gate is check out this this textbook right here. I think it's a little bit on the pricey side, but if you can get your hands on it, it is a really good book. Let me see here. I got mine about 4 days ago, and it is awesome. It's a really thick book. There is like 64 pages in here, but it covers everything, including how the mmap function syscall works. And it has a lot of really good detail. It's really well written, and it's been around for a while. It was published like 10 years ago, I think, so. Or 13 years. I'm not sure what the publication date is, but in any case, I recommend checking out this book. Link is in the description. I have no affiliation whatsoever to this book, so I'm not getting any sort of, kickback for this promotion. This is genuinely me just letting you know this is a good book to get, and it is up to you if you want to get it or not. But in any case, enough about that. Let's get back over to the guide. I think that is pretty much everything there is to say. Let's jump right into it. So, first things first, you need to determine what revision of the board you have, and the guide here does a good job of explaining how to do that. And once you have determined what you need, you go to the TerraSic resource page, and you scroll down here to these guys, the CD-ROMs, and then you download your CD-ROM. I'm revision C, and I already have it downloaded. So hold on, let me get there. So I have mine downloaded already right here, and I'm revision C. What version? Yeah, I'm on the latest version as well. Okay, let me just make sure my phone on mute here so I don't get any calls. Okay, so what we're going to do is inside the demonstration folder, inside the SOC folder, we have this GHRD folder, and this has the golden reference design in here. We're going to need that in this guide. Since I'm here, I'm going to copy this folder. I'm going to make a copy of it, and I'm going to come back out here. This is my second attempt doing this video. I created a folder called Building SOC Design Live. And then I got stuck in the middle of it, realizing I had made a mistake, and I had to scrap the footage. So this is actually my second attempt on a different day doing this recording. But in any case, yeah, go ahead and make a new folder where you're gonna have like this as like your working directory. I'm just gonna go in here and delete everything. So we're starting fresh. Okay, and I'm going to paste in that golden reference design image. By the way, if you have not completed the video in this playlist of videos, the video right before this one, the setting up the development environment where I set it up on Windows Subsystem for Linux or Ubuntu using the Microsoft Store app, if you haven't done this stuff, you need to go back and do that before following along with this guide. I feel like I should probably mention that now before we get too far into the video, just in case you thought you could just follow along right now. No, there is a prerequisite video for this video, so make sure you have that done. That will be important. Okay, anyways, so I'm just going to minimize that. Back to what we were doing. Okay, so I have a copy of the golden reference design in here, and that is good. Now, I'm moving quickly because I know that I have to kick off a build that takes a little bit of time, and I'm going to pause the recording when that happens. I just want to get to that quickly. So they're saying download it, unzip it, and put it in your working directory like we just did. And now you're going to launch it in Quartus. I just wanted to make sure I wasn't skipping a step. So I'm going to open, now that I have a copy in my working directory, I'm going to open it by clicking on this QPF file, and that is going to boot up Quartus. And keep in mind, I am using Quartus on Windows, the Windows system. It will just take a second here to boot up. Actually, I'm going to pause the recording until it says it's done loading the project. Last time I did this, it took a long time. Let me pause the recording. Okay, we are back. I don't think I'm in the way with the face cam, so I'm going to keep that up. We're going to click on this this yellow button, Launch IP Upgrade Tool, and we're going to click on this Perform Automatic Upgrade, and this is where I'm going to pause the video again. This will take how long? It depends on your system, but it's not too bad. It's not the longest one, but it takes some time. So we'll come back when this is done. Okay, so we are back, and if you got this failed, do not be alarmed. That is supposed to happen. I forgot to mention that before I paused the recording, but hopefully you did not pause at the same time I did. So let's keep on going on through. So if we look at the screenshot, we get the failed. Everything is matchy-matchy, so we should be good. And next up, we have the QSys. So let's take a look at opening that up. This is going to be, so you click close on this, and then if you go to file, you go to tools, and then we get QSys, or it should be System Planner, I think is what it's called. Go ahead and open that up. Platform Designer, that's what it's called. That's the other name for it. Yeah, open that up. It shouldn't take long to boot. And it's going to ask you to select what QSys save file you want to use. We're going to use the one included with the golden reference design. There it is. Click open. This should not take long. And then it's going to upgrade everything. Actually, yeah, I'm going to pause it. I don't remember how long this takes. Okay, I think it was worth pausing. Okay, so we're going to click close on that, and we're going to click close on this. And we're going to remove the LED PIO. Right-click remove. Now we're going to make a new component, but before we do that, we need to paste in the code here. So, in our golden reference design folder inside our working directory, we go inside this IP folder, we can make a new folder. We're going to call it custom LEDs with an S, right? Yep, with an S. And then inside there, I am going to open this folder with Visual Studio Code. And I'm going to create a new file called custom_LEDs.sv for systems Verilog. And we are going to paste in the provided sample code. So I'm not going to go over the code here, the Verilog code in here. It shouldn't be too difficult to understand. Now one thing we haven't covered yet is sequential circuits. It looks like they're doing some sequential circuits. I don't remember what we've covered so far in the Verilog development series. But regardless, don't concern yourself too much with the Verilog right now. Just keep in mind that all of the projects that we have done so far in the Verilog development series, I have you should be able to replace any of those components we made with this custom LEDs component. So we should be able to do anything with anything and interface it with C code. Keep that in mind as we keep moving forward. So we're going to copy that code, we'll paste it in here, and we're going to save that member. And we're done here, so we're going to close down Visual Studio Code. And yes, that's all we got to do. So now what we do is we switch back over to QSys, or Platform Designer, and we go up to File, and we go to New Component. And we got to make this match this picture here. Did not mean to click it. So let me see here. We're going to do... All right, hold on. Don't save. Going to... Okay. New component. And then we're going to do custom LEDs, custom LEDs, custom LED driver, hangman. And then we're going to go to File. We're going to do Add File, and we're going to go in that IP folder. We're going to go into the Custom LEDs folder, and we're going to get this Verilog code and click Analyze Synthesis File. Couldn't take long. Close that, and then we're going to go to Signals and Interfaces. And now we're going to go through all of this. Starting off with renaming this Avalon slave to LEDs, and we're going to give it a reset, and we're going to change the type to conduit. Okay, and then we're going to click on the signals. We're going to erase this, and you have to backspace it and type new signal. It's not going to be in the drop down. Go. Make sure that's there. Okay. Then select S0, and let's call it AVS_S0. And assign it a reset. So you assign it a reset right there. Once we are done, we can click Finish and say yes, save. And now we can double click on Custom LEDs and click Finish. Now it is listed right here. And now we got to connect up the clock. So we are going to get clock 0 connected to Custom LED 0.clock. So if I click on this and hover right here, you'll see that the pop-up shows clock 0.clock is connecting to the endpoint, which is Custom LED 0.clock. We want that one checked, but you can just go off of the picture as well. We're going to connect reset right here. We're going to get the AVS right here. Now lastly, we're going to click on the LEDs conduit and right click it and do connections, and then export as custom LEDs _0 LEDs. Then we're going to save it. We'll close that, and then we're going to click Generate HDL. Keep all the defaults and just click Generate. Now this will take a moment, so I'm going to pause the recording. Okay, we are back, and it says generation complete with warnings, and I don't think we need to worry about these IRQ warnings. Close and click on Finish. And now it says to make sure you did this right, go ahead and check in the... Oh, it's going to take a moment actually to catch back up. And there is the chance Quartus might crash. It's done that to me once before. Okay, there it goes. We get this pop-up notification, so click OK to that. And it's going to take another little moment to think about it. There we go, it caught up. And then under Files, we got this guy, which means we did it right. So let's go back over to Hierarchy and now double-click on your top-level entity. We're going to change a line of code so that it no longer points to LED PIO because we completely removed that, and we are going to make it point to our custom LEDs 0 LEDs new signal, which is the LED conduit that we set up. You just have to be patient with it. There it goes. All right, so I'm going to click inside here and hit Control F, and I'm going to type in LED_PI, LED_PIO. There it is. And what we're going to do is I'm going to click the Home key. I'm going to click right here actually, and I'm going to hold down the Shift key and push End to highlight the whole line. And I'm going to hit Control C, and then I'm going to push the End key and push Enter and paste it underneath. And then what we're going to do is we're going to comment out LED PIO. And then what we're going to do is we're going to change this function name to now be custom LEDs _0 LEDs _new signal. Which is exactly what they want. Custom LEDs 0 LEDs new signal. Cool, so we're going to save that. And now, unless if I've forgotten something, yeah, save it and then hit the build. So what I'm going to do is if one time I right clicked on the assembler and clicked start and it did everything. That didn't work for me last time I tried that, so I'm not going to do that here. When I did that, the whole thing crashed. What has worked for me is actually clicking this blue play button up here. Let's do that. Save on time. And this will take a moment, so I am going to pause the recording once I see that it starts successfully. I'll go ahead and pause the recording. But of course, it may also just crash right now, so I don't want to pause the recording until I get running. And I think we need to restart Quartus. I don't know, something about that QSys. Yeah, I'm going to go with restarting Quartus. It shouldn't take this long. I'm not sure what it's doing. Close, cancel. All right, let's open it back up. Since we saved it, we didn't lose any work. All right, I'm going to pause the recording until Quartus catches up. All right, so we are loaded in. Let's just double check over here, LED_PI, and our change is still there. So I'm going to close this Verilog window. Now I'm going to hit this blue play button again. There it goes. Okay, that's more like it. All right, so we'll let this run, and we will come back when it is done. Okay, we are back, and that is all done successfully with no errors. So we got to make a raw binary file, and to do that we're going to go up to File, Convert Programming Files, and then we are going to click this drop down and select RBF, raw binary file, and let's give it a unique name like custom_LEDs_live. That's the one I'm going to go with. And then down here, if you click on SOF data and click add file, and and then go into the output files folder and select your SOF right here. That is what you need. Click generate. And we are done with that. Okay, so now we are going to, let's go ahead and flash the board with this new raw binary file. So if we come over to the tabletop here, I have my board ready to go, and power is currently disconnected. And before I supply power to the board, we are going to go ahead and open up PuTTY. As you see, I already had my running, but I'm going to go down and start from scratch. Open up a program like PuTTY, switch it into serial mode, change the speed to 115/200, and then mine is going to be on COM port 3, but if you're not sure, open up the device manager program, and it will tell you, once you have your board plugged in, of course, and it needs to be plugged in on the USB UART port, and not on the JTAG programmer on the same side as the power. It's got to be over where the Ethernet port is. Okay, once you plug it in, under ports you should see USB serial port, and then it'll say what number to use. So make sure you figure that to what yours says. So I'm COM3, I'm going to click open. And then I'm going to plug in power to the board. We can see it boots up. While it is booting, I'm going to give it a larger font size. Change, let's go for 12. Login is root, password is root. I'm going to do an ifconfig to get the IP address, 192.168.0.62. Now what we're going to do is we're going to go into this folder. We just created this file right here, custom LEDs live.rbf. If I hold down shift and I right click, I can open, just click anywhere in here, right click, open PowerShell window here. And then we're going to do an SCP command, and we're going to send our custom LED. So I just typed CU and hit tab. And we want the custom LEDs live RBF. I'm going to hit a space, and then I'm going to do root at 192.168.0.62. That is the IP address that we're plugged in on Ethernet. Then I'm going to type a colon, and I'm going to type a tilde for the home directory, and push enter, and type in the password. And there it goes. So now back over here, if I hit ls-al, we have from right now, where is it? Oh, there it is. Custom LEDs live.rbf. Then what we need to do is we need to copy custom LEDs into, before we can copy it, clear ls. I have this FAT folder. If we look inside this FAT folder, there's nothing in it. We need to use it as a mount point. So we're going to go to /dev/mmc. I just hit mm and hit tab. And then we're going to do a P1. We're going to get partition 1. And we're going to mount that on FAT. Type that, push enter. Now, if we do an ls on FAT, there's stuff in there. And now what we're going to do is we're going to copy our custom LEDs into the FAT folder as a new file called SOC system.rbf. Hold on. Inside your output files, be very careful. Yeah, this file, soc_system.rbf. Don't use this one on accident. That's why we gave it a unique name. The one that with the unique name is ours. soc_system.rbf. So when we made our SD card flash image, if you have not seen that video, I'm going to put it up in the top left corner up there as a ribbon, all the way in the top left corner. way up there. That in that tutorial we create a script for U-boot, and by naming our file soc_system.rbf, specifically naming the file this and having it in the FAT, what we mounted to the FAT, having it in that location will make U-boot flash the FPGA with it. So now when I ls that folder, there it is. Now I'm going to issue a umount FAT, and then I'm going to issue a reboot. And off it goes. If I go to the tabletop, you'll notice the LEDs are not blinking, and now the LED is blinking. And back over here, we're in the boot process. So U-boot already flashed the FPGA with our raw binary file, and the fact that we see the LED blinking like that, that means we have the golden reference design image flashed onto the FPGA. So that means we are in good shape. Our golden reference design is flashed on there, and it has our custom LED component on there as well. We're nearly there. I'm going to go ahead and log in. I don't think that's necessary right now, but we'll go ahead and do that. And we're going to talk about how to do the C code. So this is our working directory. We're going to make a new folder. We're going to call it HPS_FPGA. I think that's what they call theirs, HPS_FPGA. And we're going to make a new C program called Blink LEDs. I'm going to right click on this and open it with code. Also, there is some thunder and lightning in the background. It is about to rain in Las Vegas for the first time in a while. Okay, now we have that created. I don't think it'll be too distracting on the video. We're going to copy this code and paste it in here and save it. Okay, so one of the first things we need to talk about is this header file. This header file is missing, and since it's using the quotation marks, that means that it is trying to include a header file that is in the same directory as our C program. Just in case if you don't know about preprocessor directives here, that's what that means. And the reason why it's not there is because we haven't made it yet, and we actually have to generate this using what we set up in the previous video on setting up the development environment using Windows Subsystem for Linux, or this Ubuntu app thing here on Windows. So, in order to do this, here's what we're going to do, and I believe the guide shows this as well. We are going to go into our working directory, so let's do that first. I'm going to cd into the root directory, go to the mount folder, go to the C folder, go to the users folder with a capital U, and then my user is Kirk. We're going to go into documents. We're going to go into the DE10-Nano. We're going to go into cut. Building SoC design _live. Then we're going to go into HPS_FPGA. So now we're in the correct folder. Then what we're going to do, we're going to issue this embedded command shell. And if you did everything correctly in the last video, and at the end of the last video I had you confirm this, you just type EM and hit tab, hit it twice, it'll give you suggestions. And we see embedded command shell there, so that means it will autocomplete if we type a few more characters. Then push enter. Okay, things are looking good. Now, the other thing we need is this command right here, SOPC create header files. And now use the Windows key, push the right arrow key to my terminal like that. So let's see if we got that command. If I type SOPC and hit tab, we have it, but I need to specify more characters. Now it auto-completes the full command. And I'm going to erase all of this. And I'm going to hit clear. Clear. Okay, if I do an ls, oh, sorry, we're not supposed to be in the We're not supposed to be in our coding folder. We're actually supposed to be in the Golden Reference Design folder. So I'm going to cd into the DE10-Nano Golden Reference Design. And inside here, if I do an ls, we have this system, SOC system, SOPC info. So that's where we need to be. So we're going to do SOPC, create header files, and then we're going to do SOC system.sopc info -- single hps_0.h. That's the file we're making. I'm just copying this command right here. I'm just retyping it. Module hps_0, and then push enter. It worked. Now, if it did not work for you and you have the same setup as me and it's complaining about something about not being able to find a .exe, it'll give you the file path for, and I showed this in the video where I set everything up, it'll give you the file path to this script. Go in there and remove the variable that assigns the .exe so that it never gets assigned, and then this will work for you. Okay, so if I do an ls, now we have this hps_0.h, and this is really all we needed this for. So let's type out exit, and then type out exit. We had to do exit twice because we had to exit the embedded command shell, and then we had to exit Linux. Now, one thing that might be worth noting, I have my task manager open. This VMMEM, sometimes it can have 12 gigabytes allocated, and it's a total disaster. One of the things I learned is back in PowerShell, if you do WSL -- shutdown, it'll actually stop that process and make it go away. And sometimes the process will just come straight right back. If you do WSL -L, there is this Ubuntu, and then what is it? WSL -H gives you the help. And you can do -T or -T. So WSL -T Ubuntu, and it will clear up that memory. The other option is to reboot your computer. Anyways, just randomly going down a trail there. So, back in our folder here, inside the Golden Reference Design, we now have this hps_0.h file. I'm going to copy that, and I'm going to go into our coding folder and paste it in here. So now we have that. Oh, we weren't done yet with Ubuntu. Probably shouldn't have closed it. That's my mistake. So let's close this down and let's get back into it. I'm going to launch Ubuntu. And if I do a ls-al, this .bash aliases, Control-Shift-C, cat .bash aliases. I have this export command, cross-compile. I have the ARM toolchain installed. So we are good to go. I just need to get into the directory. So I'm going to do that whole process again of mount, C, users, Kirk, documents, DE10-Nano, we're building SOC design, _live, and then HPS_FPGA, enter ls. Okay, now we're in the right spot. Now we can build this. So we will just copy this command and right click it in here and run it. Oh, maybe I forgot to install the ARM toolchain. Let me pause the recording. Okay, so I just reviewed the video from the previous video, and I am pretty sure I have that already. but let's just go ahead and get it again. Give me a second here. It's this guy. Wonder what it's going to tell me once I run this. Link is in the description. Already installed. What's going on? Now, I am pretty sure. Oh, I didn't mean to run that. Cross compile. All right, so then on this export command, what if I do Jeff? And then I run it again. It worked. Okay. Huh. Okay, so I guess if you want, you can update. Now, I thought I tried this, but it didn't work for me. .bash. You know what? We're not going to get into this right now. Just make sure you run that export command manually. I'm not going to worry about having it in the bash alias. I didn't even open the right folder. Sorry, the right file. Just forget it. Don't save. Close it down. Okay, well, it compiled. Just make sure your export command has the HF on it, and not the other way without it. Okay, let's just keep moving on. So this is the executable compiled program that we are going to run on the DE. This is the executable that we're going to run. So we're going to send that executable over to our DE10-Nano and run it. And let's see what we get. So let's do SCP blink LEDs space. We're going to send that to the root user at 192.168.0.62 : tilde. Enter. Yes. Password is root. And there it goes. So back over on PuTTY, if I do an ls, we now have this blink LEDs file here. And if I switch to the tabletop, and I kind of turn it on its side here so we can see, let me use my CC135 LPSDK module here as sort of a kickstand. I want to do a video on that in the future. Anyways, let's do /blink_LEDs. Do 4 blinks. And before I push enter, let's switch to the tabletop. And now I'm going to push enter. 1, 4. Ignore that independent blinking. And then over on the command line output, we see that blinking LEDs 4 times, and then it says done. So this worked. Let's start to talk about the code and try to understand why this worked. Let me jump back into the folder here with code. Okay. So the big idea here is mmap. We are getting a file descriptor of this device memory, and then we are using the HPS_0 header file, which is telling us what are the offsets to get to the different devices and how many memory addresses does each device take up. So the custom LED base component here starts at offset 0 from wherever our fast bridge, or our lightweight bridge is. This guide has some good references explaining it. Like, for example, this first reference really gets into it. It's sort of showing the same steps. As we scroll down here, it will basically come around to say, I can't explain mmap here. Let me see if I can do a Control F mmap. Yeah, here we go. It's going to say we need to know in order to access the IP, which is our intellectual property, or basically our component on the FPGA, we need to know where it got mapped, what address it got mapped to in the memory, and ask the kernel to give us a pointer to that memory so that we can access it. It's going to take a lot of work to go into detail about how memory mapping works in Linux, but the guide at Rocket Boards has some good explanation. So then when you go to the guide at Rocket Boards, and then you got to flip through all these pages to get to the part where it finally talks about it, and here is that page. Nope, it reset me. Darn it. Okay, so it's like basically at the end of the guide. Yeah, writing the user space application. And then here it talks a little bit more about memory map. And then one of the things it does get into is this right here, this image, which shows that all the FPGA is mapped in memory. Basically, everything is mapped in memory. That for the peripherals and everything. I know I'm not doing the best job explaining this, but this is new to me, and it might be new to you as well. I do recommend, getting this book. Getting this book and doing some research and reading on how all of this works. One of the things that came up is having memory mapped peripherals versus port mapped. I'm pretty sure this Rocket Boards guide has a link to a reference that explains that. Not seeing where it was. Book chapter on. No, that's. Oh, memory mapped I/O architecture. Yeah, this is the one. Memory mapped versus I/O mapped, and then it shows. It goes into detail to explain it. Sorry, I'm losing energy on this tutorial. But that's the basic idea. We're having our offsets generated for us automatically, and then we're using those offsets as arguments to mmap to sort of get a pointer to where our LEDs start. And it's just 8 memory addresses. So starting at offset 0, once we get to the part we want, which the part we want is going to be at the lightweight base, I'm pretty sure. We need to know the span for the lightweight bridge. And these are defined here in the code, and they were able to define these in the code because they checked the manual and they were able to give us the base address and how far out this memory goes. We need to know where to start in the memory, which is here, and we need to know how much of it to give for our memory map. And then once we have that little slice, that pointer in there, we need to add, so here's the pointer variable, and then we're going to add to the pointer variable the offset to our component. So that's the base address for our component. And it just so happens our base address is at offset 0. So we're not, this is basically taking the pointer and adding 0 to it. So we're already having a pointer to our custom LEDs. And then this span is just saying the next 8 addresses are for our 8 LEDs. So each LED's register is mapped in memory. So when you write to those memory locations, the next 8 memory locations, they each correspond to the next 8 LEDs. And so when they do the 0xFF, that is 111111, sorry, 1111 space 1111. That's writing ones to all of the LEDs at that memory address. So the next 8 memory locations are getting a 1 written to it, which will turn on all the LEDs. And that is basically how this code is working. And then they're using the span of the bridge, the lightweight bridge, to unmap. You need to unmap. You need to request that this thing gets released from your program. And I believe that is the end of the guide here. Yeah, sorry about the cross compile. Just give that a quick update and it should be fine. And I'll put the cross compile export variable description. Let me go ahead and copy this as a note to myself. And yeah, okay, I'm going to go ahead and end it here. Thank you so much for watching, and I hope you learned something, and I will see you in the next one. Bye-bye.